Hello, hello, hello! Welcome back. It is Saturday, the 3rd of January, and I hope you all had a very good New Year. We've got 2 people in the chat already, which is very good because today, what I want to go through are final preparations for the ESAT. 6 people, love to see it, because my intention for this, 10 people, my intention for this is that this is really the forum for you to ask me any questions that you have about the ESAT before you do it next week. A lot of this has been me doing live solves. It's kind of demonstrating my exam technique, which hopefully you all have found very helpful. But now is the time for me to kind of hear from you and ask any questions you want to ask. See if there's anything that I can do to help in these sort of final preparations. Seeing the numbers are a little bit weird, so we'll see if anyone's like posts any comments. In the meantime, I'm going to filibuster just a little bit and say I hope you all had a very, very good New Year. Spent mine with some friends, which was all very nice. I definitely got a little bit ill over Christmas, but nothing I couldn't manage. Sort of seemed to have come through that without too much fuss and stress. So hopefully y'all had a good sort of Christmas, New Year period as well. And you're up and ready to go, ready to sort of smash the new year. So I know I've got big plans for what I'm doing with this after we get through next week with the ESAT and the TMUA. And then we're going to be moving into the sort of A-level IB of it all, which will be very, very, very fun. But I'm very happy as well to see the back of these, because admissions campaign season is a full 6-month slog. It's a lot of work, and you got to maintain such a high level, and to sort of get to the end of it, the culmination of all that hard work, and to sort of pull it off is like such a good feeling. And then to sort of get to the other side, get to rest and relax, and really sort of enjoy the fruits of your labor, take a well-earned rest. So I do have some things I want to go through. I've got some papers open, some previous questions. I might go through papers, and rather than do a full solve, I'll demonstrate. Hello, hello. Got someone in the chat. Feel free to ask any questions. This is really the place to sort of ask any questions of me, get your final preparations in. I do have papers I can go through and demonstrate some sort of last-minute skills that you can pick up to get yourself good and ready for the papers. But obviously, like if you want to ask a question, feel free, and I'll stop what I'm doing and answer it then and there. Right, so first thing I want to talk about is, as usual with the ESAT, is the exam technique. It's making sure you're moving through the paper, answering all the good questions you possibly can, and not leaving any marks on the table. Because it's so fast, that really requires you to do that 2-step process, 2 phases, or as I call it, sort of, what do I call it? I've drawn a complete blank. It's fine. The multiple pass method. Appreciate if we can go through some electricity resistors in combination questions. Absolutely happy to do that. Have you heard about ECAA? I have a little bit. I've heard about it in the context of preparing for the math side of things, more math 2. Just found out about them, and I'm doing the advanced thoughts on it. I think it's good. I think some of the I've looked at a couple of papers, and as you get to the end of those papers, you get a few like sort of pure math logic questions, which are more suitable for the TMUA. I think you'll immediately know what I'm talking about, though. If a question looks like it's never come up on an ESAT and would never come up on an ESAT, then just don't do it. And I think that's totally fine. But at this stage, any question is a good question for you to practice your skills. So, because especially as you get to the end, you've kind of gone through it all. You've done like every available past paper. There's not that many past papers for you to go through. Yeah, you see, you just saw one a question on the ECAA talking about pigs with horns, and yes, that is very not ESAT. You sometimes get like necessary and sufficient logic, or if and only if, these sorts of things that don't really show up in the ESAT. So use your discretion about whether you think the question is appropriate, but I absolutely think there's nothing wrong with it. Going through some electricity resistors in combination. Absolutely. I'm trying to think. I know there's been a good one of those, but I think it was more section 2. I'll see what I can find. We'll have a bit of a scroll through. In the meantime, though, let's start by talking about the exam techniques. So with the multiple pass system, and I've been working on this on the TMUA as well with some people, but especially for the ESAT, if you look at a question and there's any doubt at all that you're going to get it done and you're going to get it done quickly, you skip it. So you start, it's almost like you're doing a first read of all the questions, where it's going to sort of let you know what's coming, kind of warm up the skills, and it's kind of loosen the jam jar. So when you come back to it, you're ready to use that skill. And the first pass, the only questions you should be doing are the ones you're really, really confident in. The first pass is not the time to sort of think, oh, I have to get this question, so I'm going to spend like 5 minutes on it and maybe not get an answer. First pass is like, oh no, that one, let's just bank that, bank that, bank that. Cool, cool, cool. Don't know about that one. Cool, next. And only like the low-hanging fruit, the easiest of the easy questions, you answer those ones first. That builds your confidence. It builds your momentum. It sets the tone for the paper and kind of reinforces like, okay, I'm getting these right. I feel like I can do this paper, which is really good for your like the mental game of getting through the run. And it builds up a time bank for you to then spend on the questions that you find less easy, which is super helpful when you kind of like, oh, I don't know if I can do this. And then you look in the top right and you're like, okay, I've got time. Speaking of looking in the top right, there is a timer which you should be very, very, very conscious of at all times. Because it's 90 seconds a question, you should have benchmarks for how many questions you should do by certain time checkpoints. And if you're not on pace, you should be aware of that and try and kind of make up your pace that way. I will also probably, as I think about this, I want to show you something in the UAT that I think would be very helpful. But for now, let's go back to the chat and see if there's anything to go through. Go through some questions on radioactivity and half-life. Yes, definitely can do that. Wait, so the advanced physics questions won't come up in the ESAT? No. The ESAT, if you're preparing from ENGA, it is the math and the physics from section A and only the math from section B that you should be doing. The advanced physics will not come up. Okay. Great. So I think we should go through some questions that I think would be helpful. Let me start with the ones that I've prepared just for some useful... let me just put you there so I can see you. I'm going to share... not the entire screen this time, but let's just do the window. So I'm going to share from here. Let's get myself rearranged. Turn on the little pen tablet. Because there's certain things I want you to see. From when I did my last run, certain techniques I think can be very helpful in the math. The first one, if I just have a little look, because these were both from my most recent run. I think it was question 11. So if I scroll down to question 11 here, and I'm going to do this a bit more slowly just so we can talk about techniques. Where did I stick you guys? I can't see you. Hold on, I've lost you. I want to make sure you can actually see what I'm seeing. Hold on a minute. How have I done that? Oh, now this is interesting. Hold on, let me stop sharing. Let me see if I can find you. Oh, there you guys are. Sorry, I just lost your tab for a second. All right. You struggle so much with probability for no reason. Oh, we can go through some probability. Okay, so going back into it, let's do... Okay, so right, back into it, and you can see it. Great. So let me walk you back through this, because I think this was quite an instructive question. For one specific reason. Also, doing the questions that I wanted to go through will give people more time to join and answer. Like, so hopefully, like the stuff that you find difficult, other people find difficult as well, and it can just be more instructive for everyone. So for this one, I got to a very particular point with this. Going back through it, exterior angle of a polygon with n sides is 360 over n. It's 4 larger than an exterior angle with side n plus 3. If you divide both sides by 4, you get 90 over n is equal to 1 plus 90 over n plus 3, which is n plus 93 all over n plus 3. Once you combine that, you can't see the pen. Why can't you see the pen? That's an excellent point. I can see the pen. Maybe it's a Chrome extension only. Hold on a minute. What I'm going to have to do then, please pause. Oh no, what I can do, hold on. I can draw manually. It's a little big. Let me see if I can. It'll just save me having to like reopen everything in Chrome. Because I downloaded these. Yeah, I downloaded these, and so they're kind of sitting in the default. Tech. I'm really bad at tech. We have a fix. Let's just roll with it. Right. So 360 over n is equal to 4 plus 360 over n plus 3. Divide both sides by 4. You get to 90 over n is 1 plus 90 over n plus 3. Bringing this all to a common fraction, you get your n plus 3 plus 90, which is 93 over n plus 3. Cross multiply, and you get 90n plus 270 is n squared plus 93n. Then 0 equals n squared plus 3n minus 270. Now, let's say you get to a situation like this where you have a quadratic equation that you must factorize, and you must factorize it quickly. What are the skills? Because 270's got a whole lot of factor pairs for you to run through. So what I did in my run was I realized, okay, let's start easy. It's 10 and 27 is something I know. Now, because that's a minus sign, you know that the two factors have opposite signs. One's a plus, one's a minus. And so they cancel each other out, and you get to 3, which is very close to each other. So these are 17 apart, which is too far. What I do at this stage is I just reassign factors. I take factors from here and I put them into here. So if I take a 3 across, I'm going to make 30 and 9, which has actually pushed us too far apart. If instead, what did I do? So that's 10 and 27. So I take a 3 and put it there. I could take a 2 and put it there, and then I make 15 and 18, and then bam, I found the ones that are 2 apart. You do exactly that, exactly. So factor rearrangement, and just kind of almost like prime factorization, and just distribute them until you get something approximating what you need. So I think that can be a helpful skill for quick factorizing, which can save you some precious seconds in the real thing. I think some people also enjoyed what I was talking about with, there was some factor redistribution in the physics that I did that was quite helpful. So if I scroll down to the physics, there was a particular question where calculation just got a lot easier if you used, I know the exact one to go to as well. So this was from my recent run. I'm looking for a question where you had to decide, it was this one. So this is a good one to demonstrate. So let's say we're doing this. We have a parachutist, and we need to work out which of these statements are true. So constant kinetic energy. Let's work out the kinetic energy. Kinetic energy is a half mv squared, obviously. You know that. So that's a half times the mass of 72, and the speed is 5. So if you square that up, you get 25. So again, the method I advocate for here is factor redistribution to make this really easy. I'm not going to multiply this by 25. I don't have time for this. So what I do instead is I take a factor of 4 and I distribute it across to the 25. So when I take it out of there, I'm left with 9. And when I put it into here, I get 100. So the answer is 900 joules. And that's a way to do some very good quick math that can, again, save you some precious seconds. So that was wrong there. Losing GPE at a rate of 3600, I can demonstrate again there. So GPE is mg, and it's losing 5 meters. So it's losing that many joules in 1 second. Where again, if I could take a 2 out and put it there, I'm left with 36 times 10 times 10, which clearly is 3600. So little tips like that can make your computation so much faster and easier and much more less likely to make an execution error. So that is something I really advocate for. Now, let me see if I can find, going through. So I've had specific requests for electricity questions and half-life questions. I know there was a half-life on this paper. So let me go through that. And that's kind of what I want to do today, is just go through papers and find specific questions that are kind of representative rather than do entire runs. Do you think it's a shame that ESAT rewards calculation tips like these instead of focusing on problem solving and concepts? Yes and no, in that oftentimes those tips and tricks are useful at the end of a question that is a bit more problem solving. And I think they're just kind of testing different things. ESAT is specifically testing. Hello, Disha. The ESAT is specifically testing kind of syllabus mastery. So rather than making you have a complete head scratcher that's going to take you ages to work your way through, it's more testing that you are like good to go on all of your math and physics. And so I think the ability to sort of do this stuff non-calculator demonstrates that you've taken your math seriously enough that you're not just sort of going, oh, the calculator can do it for me. So I kind of do like it, as long as not every question is like that. And I do think they have a good balance. So I'm kind of here for it. Old PAT papers were just like that. Old PAT papers were insane. Old PAT papers, like the problem solve. I mean, granted, there were some very fun questions, but some of the questions are so obscene that I take them out and use them for interview prep, because I just think there's no way you can do it unassisted. Like, yeah, the PAT is wild. And the PAT, I just feel really bad for anyone doing the PAT, because the old PAT style was completely like sort of long form written. There were maybe a few multiple choice questions per paper. Now they've swapped it. The entire thing is like multiple choice only. And they haven't released basically any past papers for you to solve. And they won't release any of the new papers. So everyone's kind of going in completely blind. It just, yeah. Yeah, the old PAT papers were great. They really were. They used to have ones like, especially with the simultaneous equations, where they had lots of you put cubes in, 3 different cubes, and it gave you relationships between the lengths of the cubes and the volumes and the weights, and they were some fun question styles in there. Definitely. Good old days. Right, let's go through this, because half-lives, I think a really good way. I've seen questions like this before. Oh, one last question before the last question on the 2012 paper with graph sketching. I don't know that off the top of my head, unfortunately, but it's good to know. I'll have a little look at that. All right, so getting into this for radioactivity specifically, it's quite common. They ask this question in like lots of different variations throughout the years, and so I've developed an idea which is just using ratios. So you start off, you have X. What are the relevant things? You have X, you have Y, you have Z. And I think the best thing to do is to think, what were the initial fractions? And then how did those fractions develop? So initially, 6 hours ago, which is we're going to use as our start time, the mixture contained the same number of atoms of both X and Y, which means that half of the atoms were X and half of the atoms were Y. So if we start with that, it was half X and half Y and no Z. Then after 6 hours, that's 2 half-lives for X, which means it's gone into a quarter of its initial value, so it has gone to an eighth. And for Y, that's 2 hours, that's 3 half-lives. That has gone a half, which is an eighth of the initial value, which has gone to a 16th. And both of those have gone into Z. And therefore, you've got to just calculate how much is left. So this is 2 over 16, which makes 3 over 16 total. So the remaining 13/16 is Z, and that's the answer. So this idea of using ratios and then tracking those as they progress through time, I think is the way through typical radioactivity half-life questions. Let me see if I can find similar questions on other years. In fact, do you want to scroll through? Yeah, go on. I was just thinking whether I should do this without showing you. But also this will show me where the fun questions are. I just want to check. When you ask about radioactivity, I'm wondering if you mean stuff like this as well, or whether you just mean sort of half-life specific stuff. While we're here, we've got some, this is a question on resistances, which I know I was asked about as well. So I will do this one while we're here. So this one, this is obviously in series, and so the resistances add in series to give, again, let's not have it be that thick. I'm zoomed in. Let's not. So you add those all up, you get 30 ohms in total. Let me just read the question and see if there's anything else I need to know. Not quite. So this was the old resistance and this is the voltage has not changed. So the voltage is V equals I times R, and using that you can work out that that is 6 volts. Now, when you remove R3, the new current is going to be from V equals IR. It's just going to be V over R, which is the same 6 volts now over 27, which is 2/9, which is 0.22, which is B. Okay. Let me continue going through, seeing if I can find relevant questions of the style that you asked for. I want to talk about this while we're here, because this comes up semi-regularly, and a lot of people don't really know about this. Because it's not often taught in syllabus. So this is basically the rate of energy transfer through a conducting solid is equal to a constant of proportionality, which is the coefficient of thermal conductivity. So it's the thermal conductivity times the cross-sectional area times the temperature gradient. For these, I kind of just use logic. Honestly, fair. And I can go through how the logic can be used, but let me at least talk about the syllabus material for anyone who needs that as well. So this is the equation that you need to know from the specification. And so from this, the power is proportional to, it'll be A, T1 is bigger, so A delta T over L, so the answer is C. If you know the equation, that becomes very easy. The other way you can do this logically is to think about what will impact the rate of thermal conduction. So that will be, if you think about it, the fact that this is a metal, you understand that what's conducting in a metal are the electrons, right? It's the electrons firing through the metal, bombarding the atoms, making them move faster. That makes the heat transfer in a metal. That's why metals are conductors, whereas plastics are insulators, both electrically and thermally. So anything that affects resistance or current flow will also affect heat flow, because the heat flows with the current. So we know that as the resistance goes down, the current will go up. And so the power should go up. So as resistance goes down, power goes up. Now, what is going to affect the resistance? Well, we know rho equals AR over L, or rather R equals L rho over A. So R is proportional to L and inversely proportional to the area. But we've just seen here that the power is inversely proportional to the resistance. So from this, you can get that power should be proportional to A and inversely proportional to L. And then by logic, you expect the bigger the temperature difference, the greater the rate of heat transfer, which is another way you could have got to C. Definitely worth pointing out while we're here, just because these are so commonly sort of requested from me. I'm going to see what else I can find. Okay, this is a great one when we're talking about half-life, because it is so easy to forget about the background rate, which is the entire point of this question. If I zoom in a little bit more so you can kind of see what's happening, we are using this to find out the half-life and the background rate. So looking at this graph, it is clear that when it decays to 0, when it is fully decayed, this constant rate that we're left with of 20 is going to be the background rate that you're left with when there's no radiation coming from your source. So the background is just trivially 20, which I expect everyone to get. But what people often do is they think, okay, let's get the half-life. The half-life is when this drops to half, so it should be when it drops to 60, so the half-life is 50. Not so, because you must always remember that not all of this 120 comes from the source. 20 of that comes from the background, 100 of that comes from the source. So when the 100 from the source decays to half of the initial value, that should be 50. And then 50 plus the background rate of 20 gives you the 70, which is crossed here at 40 minutes, not 50 minutes. Mentally visualize shifting it downwards. That is another really good idea, actually. So if you imagine starting at 100 and coming down to 0 at this point, and sort of tracking everything down by 20, that would be another way you could do this to kind of see what's happening. Of course, when this is on a computer screen, not so easy, when you can't annotate directly on the sort of graph. But this is another way you could get to the fact that it is 40 and not 50. Certainly worth going through that as we see it. So now, let's see what else I can find. I'm looking specifically for anything to do with radioactivity and half-lives, or this to do with sort of resistors in series and parallel. Now, this you can do in several different ways. One way of doing this is to spot that these are in parallel. So when they are the same resistance, it'll be 1 over R plus 1 over R, which would become 2 over R. And when I flip that round, you get R over 2. So this is an equivalent resistor of R over 2 for this being R. Now, the total power supplied by the battery is 18. We know that P is equal to IV or I squared R or V squared over R. I like using, most of the time, you're using I squared R. Certainly whenever you're working out the power derived, like the heating power of a circuit, you're using I squared R. But in this particular case, because the current depends on the resistance, it's not as good a measure here as the constant V. So P here is inversely proportional to R. So the smaller R is, the bigger the power is going through that. So you could consider, and the power dissipated is heat. That's exactly when I said we would use I squared R. Sorry about that. So I'll do this a couple of different ways. So the first way is to recognize that if this R, okay, let's do it this way. Let's do I squared R. So if P equals I squared R, then for a constant current, as these would be for sort of being in series now, this one has half the resistance. Oh no, that's not great. How did I do this? How do I explain this succinctly? Oh, you can solve it using ratio of voltage. Yeah, you can. I think I like thinking about the current here. So the fact is, this is going to split. If this has got a current, which I will call 2I, for reasons that will become clear. Draw, come on, you can do it. Because these resistors are the same, we know that current is going to split equally between the two branches. So there will be a current of I going through both of these. And then this will become 2I when it recombines going through Z. So the power going through here is I squared R. The power going through here is I squared R. And the power going through here is 4I squared R. And therefore, it's a sort of 1:1:4 ratio. So if it's a total of 18 being distributed across all the resistors in that 1:1:4 ratio, which would be 6 in total, we can see this will have to be 12 watts and these would have to be 3 watts each. So that's one way of doing it. I want to see if there's any other way of doing it. The problem of using the equivalent resistor here is we want to find X. Yeah, 300 subscribers. Yeah, I did. We're slowly getting there. And I think it'll like probably take up once we get to sort of like the A level, when we sort of a wider audience of people that I'd probably be speaking to. But to be honest, I just started this as a little pet project for maybe people who were doing ESAT just for fun. So the fact that it's 300 at all, I'm super chuffed with. Let me see. Is there a better way of doing that? Like I say, the problem of doing the equivalent resistor here is it kind of treats that as one equivalent resistor when we actually want the X to stay where it is. So doing that, I don't think is the best here. Although it does kind of track in that, in this case, no, it doesn't track by what I was trying to do. Which is faster? So yeah, everyone's got different styles for this. I know my style there is to sort of split it out and just think about the sort of ratio of powers. I'm just trying to come up with alternative methods that people might prefer. So here, well, so okay. So here's another way you could do it. So you've got your R over 2 versus your R, which means if we split the, if we think about the fact that those equivalent resistors are in series, then we know that the voltage will distribute in proportion to those resistors. So if this is, for instance, 3V, then 1V would be dropped. I'm just going to erase this just to sort of clear everything up a little bit. So using a voltage pathway, this would be an equivalent resistance of R over 2. And so you could consider this to be, I'll get rid of current because I'm not using current this time. And in fact, let me get rid of the 12 because spoilers. What we would have here is that because that's a 1-to-2 ratio, this voltage would split into a 1-to-2 ratio. So it would be V across here and 2V across here. And then again, we can use this relationship to say if R is constant, then this power would be V squared over R. This power would be V squared over R. And this power would be 4V squared over R. Which is another way of getting that if this, it's sort of 6 V squared over R's in total, split, and then the 18 watts split between those again makes each one of those 3. So you can again get to 3 watts, 3 watts, and I'm being an idiot, 12 watts. So that's how you can get there via voltage, which might be to your preference. I wouldn't recommend doing P equals IV there. Someone says, they're a tad late. I'm redoing the questions before you go through them, but it's just the half-life stuff, nothing to do with alpha, beta, gamma. Cool. So whenever I find half-life stuff, I'll point that out. Okay, so yeah, because these can be really tricky, these circuit questions, if you don't spot the trick. So I totally get why you're requesting that. So similar here, actually. I remember this one being a bit difficult. If we make, for example, okay, someone's got an alternative pathway for this. So let's say here. So let me erase what I've done so we can make room for the new idea. Okay, so if we make, for example, XY is one resistor, and the voltage would be 1 to 2, so we know X has a third of the voltage. So I think that's kind of what I did. So if that's 3 volts, then because that's half the equivalent resistance, it'll be voltage across there, 2V across there. Huh. So we know X has a third of the voltage, so I can't quite make sense. Like, I'm sure this makes sense in your head, but I can't quite make sense. So power is V squared over R. And R is, oh, total. You're talking about total. Right. I'm with you. So you're saying total power, because, oh, okay, I see what you're saying. So you're saying, yeah. So you're right, that's a third pathway. Okay, let's try it that way. So you could say that these are, again, equivalent resistors in parallel, identical resistors in parallel. So when we treat them as an equivalent resistor, that would be R over 2. compared to this R. Then you're right. If we consider R total, that would be 3R over 2. And you can do P total equals V squared, which is just the voltage, over R total squared, not squared. Which when we put in that R total is 3R over 2, would make this 2V squared over 3R as the total power. And we want the power in X, not the power in total. Where this is V over 3. It's not V over 3, though. It's V over... We know that... Okay, which is equal to 18. Got you. I like that. I like it. So you're saying... Oh, I think I like it. So then you get V squared over R is equal to 27. But that's V total. And the power, I suppose you can then argue that the power in here, because the voltage is a third of the total, so it would be... Yeah. And then our Vx, it's not my preferred path, but it totally is valid. Because you got to then say that Vx here is a third of the V total. So Vx squared over R would be a ninth of Vt squared over R, which is a ninth of 27, which is 3. So I suppose that is another way of getting there. Yeah. And this is the funny thing about circuits. There are usually so many different ways of going about them that as if you can just find any path that works for your brain, you're probably doing just fine. Okay, so we're going to move off from this one now because this really is a juicy question. There's just a lot in it. Similar here, I find these kinds of things with graphs can really throw people because they contain lots of different situations in them all in one go. So if I consider this for a second, we have a filament lamp and a variable resistor. The graph shows the voltage current resistant characteristics of the filament lamp. The resistance, let's just draw this out so we can kind of see what's happening here. So we have a filament lamp and a variable resistor. When the variable resistor is 4 ohms, the current in the lamp is 2. When the current in the lamp is 2, the voltage in the lamp is 6. And for a current of 2, and so V equals IR, that means this is a fixed 3 ohm lamp. When the resistance of the variable resistor is 0, that becomes, well also, hold on, that's a 3:4 ratio. And so that will have to be 8 volts across there, making it 14 volts in total. And when this variable resistor zeroes out, we now have 14 volts. Which makes the current through it 3. And P equals IV. Oh, because this is not a fixed resistance, of course. It is that resistance at that particular current, but that does not mean it is that resistance the whole way through. And this is where this can get a little bit tricky. It's just thinking about using the graph. So the current here at 14 volts, when all of 14 volts are going through the filament lamp, the current becomes 3. So it's 3 times 14, which gives you your 42 answer. This is the end of that one. Let me just go through, see if I can find any good more in the physics in particular, which is where people seem to want to be. Specifically when it comes to half-life Or, again, I know you didn't ask for this, but I think it's really important, these graphs. Okay. So here, diode is connected in series with a resistor and a 6-volt battery. The current in the circuit is 8 milliamps. What is the resistance of the resistor? So if the current is 8 milliamps, we can track and see that that voltage across the diode is going to be 1.2. Again, let me just make these a bit thinner. So if the voltage is 1.2, then the voltage on the resistor, hold on a minute. So it's a 6-volt battery. We're going to have a resistor, which is going to carry the other 4.5 volts. And then we're going to have our diode here, which is going to be at 1.2 volts. So there's 4.8 volts on that. And the current is 8 milliamps. So V equals IR. R is equal to V over I, which is 4.8 all over the 8 milliamps, so 0.008. Or rather, 8 times 10 to the minus 3, which then we can bring up and do 8 times that. So it's 0.6 times 1,000, so it's going to be 600 ohms, which is F. Going through now, trying to find more of the ones that are relevant. And again, we have this, you see, they really like this question. This is another one going through that equation, that sort of, the rate of energy transfer, dq dt, again, is Ka times the temperature gradient. So you can see it being tested in consecutive years there. So the alpha, beta, gamma you're fine with, but it's the half-life specifically that you wanted to go through. All right, this is another one of those sort of like resistors in series and parallel. So what's the voltage across here? Here's how I would cut this. This looks like I'm gonna, okay, so I'm initially gonna treat this again with currents. This is where my brain goes first, because I know that because the voltage across these parallel branches will be the same, but this has double the resistance, it will have half the current. So the current is splitting in a 1-to-2 ratio, which means if I have 3I going in, then 2I goes up here and I goes down here. I did resistance ratios here too? Probably. That could work. Well, because that's, if we're going to treat that, then we've got 1 over R plus 1 over 2R, which is 3 over 2R. So the equivalent resistance is 2/3 R for this parallel array in the middle. So then we have R plus R. So that 2/3 R plus 2R, which is 6/3 R, gives you your 8R over 3 as your total resistance there. Alternatively, we could say, if we consider the resistance ratio, because we know that these equivalent resistors would be in series, that would be R with a 2/3 R with an R. So in other words, it'll be split in a 3-to-2-to-3 ratio. So if that's 1 volt, that's 1 volt, it's 2 volts in total, which means these have to be 3 volts, this has to be 3 volts, and so it's just 11 volts, I think. Is that an option? That's not an option. Got it wrong. Go me! Why did I get that wrong? Can someone point out why I got that wrong? I'm sure I got that right in the actual run. Because today I'm going through it not so much an exam mentality. This is more sort of, validating that, yes, these are difficult. Let me just rerun this, because I'm sure I've just done something silly. It also gives you time to sort of put in the chat if you spotted the silliness that I just engaged in. So in the parallel branches, if we have 2V total, then we can assign that to the resistance in the parallel part and set up ratios. Well, if we know this is 1 volt, we know that's 1 volt. So we know that's 2 volts. And so that's 2 volts between the entire thing here. That's 2 volts at a resistance of R. So in fact, I think as well, why don't we introduce this as a trick? If they're all the same, why don't we call them all 1 ohm? Because then it can work. So if that's 1 volt and 1 ohm, then that would be 1 amp. And this would also be 1 volt, making that 2 volts, making that 2 amps, making this 3 amps, making this 3 volts, making this 3 volts. Oh, did I just add them up wrong? I did just add them up wrong. I didn't. What did I do? I said, hold on a minute. I had that right the first time. No, don't let it be my mental math. That's embarrassing. No, guys, I was right, and it was a 3 to 2 to 3. But it turns out when you add those up, you don't get 11. You get 8. Well, because if you're thinking about this, like let's run back through that. So the R parallel, it was 2/3 R from what I did before. So it becomes, oh no, you're right. It's not 2R, it's R. So it's R to 2/3 R to R, which is a 3 to 2 to 3 ratio across these bits. So if that's 1, that's 2 in the middle. These both become 3 volts very easily. Not sure if someone mentioned already, but you can go through. Could you go through the DOE? I'm not sure exactly what you mean by that. Some probability as well. Probability I can definitely find. So I think that's, yeah. In other words, like circuit stuff can be really trippy, but like if you kind of take it a bit slower and a bit more locked in than I'm doing right now, I think you should be fine. Let's see if I can find any. Yeah, again, this is sort of another one of these half-life equations which requires these ratios. So let me demonstrate my technique here again in case that helps. So a sample initially contains equal numbers of X and Y. So it was initially a half to a half. Isotope X has a half-life of 3 years and decays into a single stage into Y. So in 6 years, which is 2 half-lives, that becomes a quarter of the original, which is an eighth, which means this is now 7/8. And so it's a 1 to 7 ratio, the end. That's how easy it gets if you use that technique. All right, let's go and find some. I'm still, if you can comment again, if you can go through DO, E. Not sure what you mean by that, but probability I can absolutely find. Let me see if I can find anything good in the math for you. Let's see if I can find probability. And I'll also point out, by the way, while we're okay, probability. Great, let's do this. So here, box A is 10 balls, of which 6 are red, 4 are blue. Box B is 15 balls, of which 3 are red, 12 are blue. All the balls are identical in every respect, apart from color. One box is chosen at random by tossing 2 fair coins. If both are heads, then you pick A, otherwise it's B. So in other words, there's a quarter probability. It's just too many words? Right, well, let's break this down. One ball is then randomly taken from the box. The way to think about probability is think about and or. What is the probability that a red ball is taken? Well, that is the probability of box A and it's red. So let's say, in other words, if you can think in your head about what the logic is. So the situations are either it's A and red, or, in fact, let me put this in capital letters so it's like really obvious. Or you're picking from B and you get red. Well, just tidying this up, and you get red. So the reason why I underlined these ands and ors is whenever you see an and, think times. Whenever you see an or, think plus. So in this case, the probability of picking from red is a quarter, which is the probability of getting 2 heads. So it's a quarter times getting a red from A, which is 6 out of 10, plus probability of going from B, which is 3/4, times the probability of getting a red from B, which is 3 out of 15. We can cancel that down and get 1 and 5. We can cancel that down and get 3 and 5, which is 3 out of 20 plus 3 out of 20, which is 6 out of 20, which is 3 out of 10, which is C. So that's how I like to think about probability. Someone asks, just to clarify, in the ESAT, are there only 4 options for each question, or are there more? There are more. There's, in fact, I would expect there to be about 8, typically. They really like to throw you off, and they anticipate possible execution errors that you make and purposely put those in as options just to trap you, because they are deeply unhelpful people. So yeah, I would expect 8, somewhere around 8 results to choose from. 6 to 8, that kind of thing. 4, you'd be very lucky. Let me see if there's anything, because there's one more skill I really want to go through in the math, but I want a good question to demonstrate it. This is not the one. First of all, whenever you see anything with algebraic fractions, make sure you fully factorize and simplify before doing any other nonsense. So here, making sure that you cancel those down. First of all, factorize that into 3x plus 1, x minus 1. So that those cancel down. So it really simplifies to 4 minus 1 over x into x minus 1, which is just a lot easier to combine. So you get your 4x squared minus your 4x minus 1 all over x into x minus 1, and you get d. So not too bad if you just fully factorize before you do anything else. There's one particular, while we're here, let's go through the math. Finding any weird probability questions, and also anything I think is particularly helpful. Because I want to show you, you got to get good at your triangles. So the scaling triangles are something I really want to find. I do love that. Apologies for the delay while I find a relevant question. I'm seeing probability again, and again, words and algebra. This can be off-putting. You can select tomato, sauce, mayonnaise, both, or neither. This looks very Venn diagram-y to me. Mayo, both, or neither. 3n plus 1 students select tomato sauce total. 3n minus 1 students select mayo only. There's 7n plus 5 in total. The probability of selecting only mayonnaise. Oh, that's too easy. Although, maybe not. Because you get your 9n minus 3 is equal to 7n plus 5 very simply. And then you get your 2n is equal to 8, so n is equal to 4, no problem. So that becomes 11, no problem. And this becomes 33, no problem. But then, oh, sorry, I've misread the fact that n students select both. So 4 select both. Oh, this was too easy. And then 13, and then that's 9. So it's 9 out of 33, which is 3 out of 11, which is A. That's probably not what you were looking for. But I'm looking for, very specifically, a 30, 60, 90. This is probably more like it. Okay. So let's, again, think about the sort of ands and or of the situation. Red, then the child stops taking sweets. If green, it's not replaced, the child takes another sweet. What is the probability that the child takes more green sweets than red sweets? Well, let's think about how to do that. That is, well, think about how that is done. That is, think about all the possibilities. I can get red and then I stop. That does not work. I can get green, then I get red, and that does not work. Green, green, red. Green, 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 red. And you can see there's going to be loads and loads of these probabilities going up to getting all 6 greens and then my red. Now, if in any probability question, if they're asking you about all the other options, they're probably asking you to do 1 minus these guys. So it's going to be 1 minus the probability of getting red minus the probability of getting green and then red. So it's 1 minus 6 out of 12 minus, and the probability of getting green and then the 6 reds out of the remaining 11. And this is going to get you your answer. So importantly, that cancels down to 1, that cancels down to give us 3, and that cancels down to give us a half. So out of 22, it's 22 out of 22 minus 11 out of 22 minus 6 out of 22, which gives you 5 out of 22, which is B. So again, thinking about all the different scenarios, the ands and the ors of everything. And looking in the math here, just going through a few years worth of stuff. I want to find... I'm surprised not to see this is. I feel like this is more frequently tested than what I've been showing. Because these 30, 60, 90 triangles come up everywhere. So something like this, where you know you're splitting this out into your equilateral triangles. God, I messed that up, didn't I? Close enough. And then splitting each one of those up into 12, so making that 6 and 6. And lots of these questions rely on your understanding of the 1, 2, root 3 triangle. And so if you can start from that and then you can scale up to the triangle you actually have, you should be fine. In this case, you're multiplying by root 3 and by 2. So you do that everywhere. Multiply by 2 root 3, 2 root 3. And then you can get the area of the triangle very easily as 6 root 3. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those to give you 72 root 3. So these base triangles, your 30, 60, 90, 1, 2, root 3, super, super helpful. I think it's paper's also got, if I can go into the, I think it's come up in some math 2, some good ones in math 2. In fact, it might be a good reminder. Let me get rid of that. I'm going to stop sharing that screen for a bit. I'm going to find, let's see. I'm going to try to download the 2016 because I remember I used the 2016 paper quite a lot. What if I drag this across, for instance? The reason why I like the 2016 paper is because it's got this very particular question in it, which is the last one I really want to go through before I take some sort of comments from you guys. NSAA. Because I think it's honestly the most important skill. So this is one I haven't done as a live solve. Because I've used it so much, like I just know all the questions by now. But it's one of my absolute favorites, this one. So this is from a math 2. I'll start sharing my screen now. Don't worry, I know you can't see it just yet. So this question I think is so good for demonstrating the importance of these 30, 60, 90 triangles. So in this case, if we want to find the shaded area in that is given in square centimeters, if I think about, okay, this time, I know it's great. Yeah, you've stopped being able to see this. I don't know why. Oh, maybe because it's, hold on a minute. Let me try one more thing. Because you used to be able to see it. So if I do entire screen, I think it's because it's a separate application. There you go. That was the problem. See, every little mistake by the time, I'm slowly becoming a bit more of a tech expert. Love this question so much. Way this works. draw it to there, draw it to there. That is 10, that is 20. And immediately, this is all you need to think, this, if that is 10, 20, that is a scaled up 1, 2, root 3. So this becomes 10 root 3. Scale factor is multiplying by 10. And so immediately you get that that's 10 root 3, which means immediately, and that's because that's 90. Immediately, this becomes half base times height is 50 root 3 to give you 100 root 3 in total for both triangles. And then immediately, because you know this is a 30, 60, 90 triangle, you know that's 120, which is a third of the total circle. So it's pi r squared, a third of that, and you quickly get to 100 over 3 into 3 root 3 minus pi. If you really know that resolving 30, 60, 90 triangle, this question just falls apart in such a beautiful way. There's another question like that in another year, and I don't know specifically which one it is, and it's probably not worth wasting your time going to find it. Because it's in a math 2. Can't remember which year, but I will have done it on a live stream because this is the only one I think I haven't done on a live stream. And it wasn't in here, but it's a glorious one where you have to do a similar thing with coordinate geometry. While we're here, just one last thing about coordinate geometry, in case it comes up, because I quite often see, so you have your coordinate geometry, you have like, let's say you've got a line, y equals, I don't know, minus 2x plus 3. So you know that's 3, you know that's minus 2, and it's asking for the shortest distance from the origin, something like that. So these types of questions come up kind of a lot. Just remind yourself that this, whenever you have a sort of 2 lines that are perpendicular, one of which is going through the origin, that splits this up into lots of similar triangles. So if that is theta, that is 90 minus theta, that is theta, that is 90 minus theta. So it means the whole thing, we can work out that this would be 3 over 2. So we have the big triangle, which is 3 over 2. And so let me label the points, in fact. So A, O, B, C. We have the AOC triangle. Remind yourself that that is similar to ABO, and it is similar because that is 90. That is theta down there. That is theta down there, and that is also similar to COB. And this can sometimes save your life. You can also use inverse Pythagoras, and it's so much faster, just one equation. Ooh, quick question. Do you think it might be useful to just random guess 1 or 2 questions to focus more on getting the others right? Yes, let's talk about that. Because now you're getting into the sort of what I want to talk about. That's the sort of conceptual stuff I want to talk about. Let's finish off by talking about exam technique. So we've spoken already about the multiple pass system, the fact that you want to be very selective about your first question to really set the tone. In your first pass through, only select the really good questions that you know you're going to get right, that you could just bank. That way, like, you've really increased your probability of getting like the maximum number of marks in the early stages of the paper. And if you are guessing at any point in the paper, it's only on questions you're not that confident on. Now, let's say you can feel yourself burning time. You've got like 3 questions left. You've got 4 minutes. You know you're not going to get through all of them. Maybe there's something you can do. Maybe there's some decision that you can make. Hold on. I'll start sharing my screen again so I can demonstrate this principle. I'm just going to pick a question at random, paper at random. So let's say we've got a particular type of question, which is asking for some decisions, right? So this one, let's use this as an example just because I'm here and for no other reason. So let's zoom on this, because you have 2 decisions to make. You have one about the electromagnetic, one about the longitudinal. A person detects only 2 waves unaided. So you might go, okay, I don't know, I don't have a lot of time, but I know that it's like 500 nanometers is visible, so I know that 4 is right. and then I'll guess from the other 3. So I know that 4 is right. So what you can do is to sort of process of elimination some of the way, and then you're just coin tossing between A and E if you don't have that much time to calculate which of those you can hear. So something like that, if you're forced into a guessing situation, maybe make one educated guess that eliminates some impossibilities to improve your guessing chances, and then guess. As well, if you look at a question and you're like, there's just no way I'm going to get there in time, again, tactical guessing is not the worst idea, especially if you can make some very quick simplifying assumption that eliminates some possibilities. Absolutely. And every single thing you do, like every single question should have an answer in it by the time you're done with the paper, because you never know, you might be getting it right. So definitely make sure you have time to submit an answer for everything, because it's just worth it. Actually, the final thing I want to do is to show you guys something very, very important about the UAT website. Because I found a lot of my people did very, very, very badly in October in Math 1. And I asked one of them why, and he said, let me see if I can find it. Yeah, so I've got my ESAT Math 1 open now. If I start sharing the screen, he noticed that this actually did happen in the real thing. So it's desperately important you know this exists. So he knows for certain, because he went to check, that he did that. And then he clicked somewhere else on the screen. And look what just happened. Look where I clicked. And it changed the answer. The reason why I did that is because this bubble stretches the whole way across the screen. So if I click there, it still goes. So if you were just like, you're clicking and then you do something and then you click to refresh the mouse, it might change your answer. And he knows that that happened to him at least once in that exam. So before you move off, make damn certain that the answer you wanted is still there. You would use N on the keyboard. So let's test that out. So let me just wake my keyboard up. So you are allowed to click your answer and then click nothing else, click the letter N. And on mine, that doesn't move to the next thing. But maybe in the real thing, you can click type N to go to the next answer. But the point still stands. Make sure the answer you wanted to submit is actually still highlighted by the time you move off the question. Otherwise, you won't notice that it's changed and you won't know to come back to it. So it worked in your path. I'm sure that sort of solution exists. It's just tech hates me. So that's the last thing I wanted to say. Make certain that everything is submitted appropriately before you move off it. All right, team. I think that's about everything we need to say now in these final stages of preparation. Hope you found all of this useful. Mainly that exam technique, like knowing how to go through the passes to make sure you see all the questions and don't sort of think, oh, there were like 5 questions at the end and I could have done some of them. Like, it's making sure you see them all. So all the good quick ones you get under your belt to just make sure all your time is spent getting maximum number of marks possible. So that exam technique is definitely the #1 thing I wanted to talk about. Hopefully you still found it useful. The little tips and tricks I gave you when it came to the math computation, the 30, 60, 90 triangle, the probability stuff, the half-life stuff, and the circuit stuff. Do let me know how it goes. I'll keep a sort of. I always track the comments, especially at this stage, just to sort of see how people are doing. In the meantime, hope it goes well for you guys. Good luck with it, and I will see you guys on the other side. Ooh. Do you have some quick suggestions to not lose too many time on understanding a long question? Skip it. Come to it in the second pass. Because remember, your first pass is just for ones where you look at and you go, yep, got this, got this, got this, got this. Because the good quick ones, you'll be doing them in less than 1 minute 30 per question, which means by the time you finish them, you might have done like half the questions, maybe, let's say. So you might have done 10 questions, or it's 27, isn't it? So let's say you've done, even if it's only 10, let's say you've done 10 questions, but you've done them in 10 minutes. It means you have all that extra time to spend on the remaining questions, which means you feel less time pressured and you're more able to slowly read the question, process it, and get it right. So it's not even about the time, it's about your understanding of how much time you have available. So if you leave the longer questions for your second pass, you'll just feel like you have more space to breathe. So that's my advice there. Use your time judiciously at the start of the paper so that you don't feel rushed by the end. Great. So with that, oh, I fear my mind will go blank on every question. No, that is another good reason for the multiple pass technique that I use. Because you watch my live solves, right? I purposely made it difficult by doing the really hard questions at the back first, because I thought exactly the same thing. And I look through and I go, it's not even I can't do this question. It's I don't like that question. I don't like that question. And you wait until you see a question, you go, oh, I like that question. Because then you get it, you know you've got it right. And that sets the tone for the paper, right? And then it gives you that feedback. Ah, okay, this is a safe paper. I can do it. So the question you choose to do first is the most important decision you will make in the entire paper. So keep skipping until you see one that you like. And then you're like, great, that's the one. And then you get in, you get it, feels good, sets the tone, eases you in. Then you start getting the ball rolling. And once the momentum is gained, you don't lose it. So that's another reason for going through that multiple pass technique. Okay, right. I impart my wisdom onto you. You guys should do fine. And just employ good exam technique and you will be fine. I will see you guys on the other side. Thank you very much for sort of watching and sort of bearing with me as we've gone through all the preparation. I really hope it goes well for you guys. And thanks for being sort of around for my first ever sort of admissions campaign. I'm going to go live. You are very, very welcome. So I've just got a couple more lives to go for this admission season. I'm going to be going live tomorrow, I think doing a very similar thing to today on the TMUA, because I don't think I have time in the evening. Oh, no, maybe I could do it on the 6th. So tomorrow I'm definitely going live. I'm either going live with another sort of Q&A about the TMUA, or I'm going to do a final live solve on the TMUA. And then at one other point this week, I'm going to do one of each. One live solve, one questions on the TMUA. And then we're done. Then we're moving into A-level. So you are very, very welcome, guys. Hope you get a good paper. Just be really on top of your execution. You guys should be fine. Work hard. Have fun. Don't panic. You guys are going to be fine. Take care, guys. And I'll see you when I next see you. All right. Bye-bye.